And we're going to create a Lotto field bigger than K, and over which it's easier to tell whether the two quaternions are isomorphic or not. And at the end of the day, I'm going to prove a big theorem which says that if the two quaternion algebras over Q, they're the same after passing to this sort of bigger field, then these two quaternion algebras themselves will be isomorphic over Q.
So sorry, I'm really confused about that. So the quaternion over Q AB cancel with R does not just give you R AB, right?
It does.
But then the isomorphism carrying Q AB, if A is
Yeah, but okay.
if A is positive, B is negative, the A and negative AB will be positive and positive.
I think the confusion point is that
Yeah.
even if you know that after base change they're isomorphic,
Okay.
you cannot sort of reduce back.
I mean,
Is that
QAB and QA negative AB are isomorphic. But if A is positive and B is negative, then QA negative AB is Q positive positive.
yeah, they're all isomorphic to the matrix algebra.
Oh, I see. Okay.
Yeah, the condition you need is that both of them are negative, but
Yeah.
if you could have one of them positive or both of them positive, but that, in that case you can't make it.
Oh, I see. I see.
Capture. These two are isomorphic does not imply that these two are. This is much stronger statement. Other questions? Okay. Now, let's move on to the next topic. Constructing one of these bigger fields, namely Q. So the idea is that Q is sort of the central object of number theory. And the way we get the real numbers, or somehow new understanding I'm trying to sell here, is that the way we get the real numbers is because we put Q, we put kind of a metric on Q and take completion. This metric is usual absolute value. And now what we're going to do is that we'll ask, are there other metrics we can put on Q that will give us something more? So it turns out that for each prime P, there's a new metric we can put on to give us these sort of so-called PI numbers. So P is a So let's do this. Just psychologically easier to define two things together. Instead of just norms. So we define something that will give you the norm. We'll give the sort of matrix structure later. So we define a so-called periodic valuation. This periodic valuation, you can think of it as a map from the rational numbers to integers, or kind of a symbol, just infinity. So this is defined as follows. So the valuation of 0 is considered, maybe I should have plus infinity. It's just a symbol, because 0 always behaves something simple strength. And for any integer n, I can always write n, a. I always write a as p to the n times u. For, an integer n bigger than 0 and the p does not divide. I can factor out the p part of it. So I'm just going to define the periodic valuation of this integer a to be this exponent of p, namely n. So I define to be the exponent of p. So in general, first, second, in general, for a rational number, I just define periodic evaluation to be the periodic evaluation of A minus the periodic evaluation of B. You can see that I didn't even require that A and B to be co-prime, but that's fine. I mean, even if you multiply A and B both by P, what's going to happen is that periodic evaluation of A and periodic evaluation of B will be both increased by 1. So the increase cancel out. This doesn't have to be the minimum presentation of the rational number. So in some sense, roughly speaking, periodic evaluation is, in some sense, a p-divisibility of a rational number. So once we have the periodic evaluation, we can define so-called periodic norm, or sort of periodic distance. Or rather, this is sort of the sentence of p size of rational numbers. Earlier on, we talked about the usual absolute value that considers some sort of real, like the actual size of the actual size of the number. But now this size only concerns the prime p. So I'm gonna write looks like the absolute value, but put p in a subscript. This will map from Q to non-negative real numbers. I'm going to define it to be p to the negative periodic evaluation of x. Namely, so periodic evaluation of x tells you how divisible it is by the prime number p. So this means that if it's more divisible by the number p, it becomes smaller because p to the negative power of the evaluation. So here's a couple of examples. First of all, the periodic evaluation of the weird number 0 is p to the what? To the negative, the periodic evaluation of 0 we define to be positive infinity. Now I put a negative sign, so I'm going to do p to the negative infinity. This is just a symbol, to make you easier to remember. So p to the negative infinity, meaning that's extremely small. So 0. And I can do, for example, p equals 5. Just give you a number. For example, b5, 5 adding evaluation. For example, 14 over 75. 14 is prime to 5, so it doesn't contribute to the 5 adding evaluation. But the denominator 75 is divided by 25 exactly. So you get negative 2 because this is the denominator. So the 5 adding evaluation of 75 is 2. If 75 is the denominator, you get negative 2. And now the norm of 5 of this number will now becomes p to the negative of negative 2. So this could be p to the 2, which is 25. If you have 5 in the denominator, the norm becomes large. So when you have 5 in the numerator, the norm becomes small. And if it's more divisible by the number p, the norm becomes very small. It's a little counterintuitive in the sense that if you think it's more divisible by the prime number p, it will be very large in the usual sense. So say 5 to the 100, it will be, I don't know how many digits, maybe 60 or 70 digits. But in terms of 5 adding norm, it's going to be very small. It's going to be 5 to the negative 100. So I'm going to use this periodic matrix to define, use this periodic norm to define a metric. So I have two numbers, x and y in Q. Their distance is defined to be the p-adic norm of the difference of x and y. This is usual thing. So let me draw a picture of where these numbers are, like what the distance is on the picture. I think you probably have seen it at various places. So this is number 0. And number 1, the distance between 1 and 0, I know the green color is better because that on the camera. So this distance is 1. Because the difference between 0 and 1 is 1. It has valuation 0 and p-adic norm 1. Similarly, point to, oh sorry, I'm doing a picture for p equals 5. Actually, you know what, sorry, let's change my mind. Let's do p equals 3. So distance between 0 and 1 is 1, and also 0 and 2 is also 1. And now where should I put 3? The distance between 0 and 3, the difference is 3, is exactly divided by 3, right? So according to our formula, the 3-adic norm should be 1 over 3. So actually closer to 0. So let me just draw maybe 3 here. So this distance is 1 over 3. And what about 4? Well, the distance between 4 and 0 is, the difference is 4. So the 3-adic valuation is 0. So distance is 1. But 4 is closer to 1. Because the distance here is, difference here is 3. And 5 is over here. That's 1/3. This is 1/3. If you want to know what's the distance between 0 and 4, it's also 1. Okay? So what about, okay, you can do sort of same thing, 6, 7, 8. And what about 9? 9 is even closer to 0, so 9 is somewhere here. This is 1/9. And 10 is over here. And over here you can also have some sort of 12, which is closer to 3 than to 0, but still kind of far apart from 1 and 2. Well, somehow the picture looks like kind of a cluster of things that's congruent to 0, and clusters of things that are congruent to 1, and clusters of things congruent to 2. And for each cluster, there's a kind of finer cluster, like sort of finer chunks over here. And each sort of finer chunk, there are sort of 3 parts, which are somehow further divided. And it's I think it's a perfect illustration of fractals. But it had nothing to do with fractals. Sorry, cross that. I'm not sure. You know, in mechanics, you never know what's going to happen. Alrighty. So now getting to some key properties of the valuations and norms. The first thing I want to point out is that p-adic valuation of the product is the sum of the p-adic valuation. That's easy to see how much x is divided by p, adding how much y is divided by p is exactly how much their product is divided by p. So in terms of norms, the addition in the valuation turn into the product of the norms. They look very familiar. It's the same as mutual absolute value. Second one is an interesting one. If you look at the p-adic valuation of the sum, what you get is at least the minimum of the p-adic valuation of x and the p-adic valuation of y. Why is that? Well, that's because say n equals to the minimum of this thing on the right. What do you see from this? If n is minimum, n is small, I guess, excuse me. What it says is the p-adic valuation of x is at least n. That means p to the n would divide x. Because the valuation of x is a p divisibility of x. If it's bigger than n, then it's p to the n that needs to divide x. And similarly, p to the n would divide y. And this would together imply that p to the n divide x plus y. But it's possible that, of course, there's some becomes more divisible by p. So you have a strict, possibly a strict inequality here. And we can turn this around from the evaluation to the norm. So this will give you x plus y, the norm of x plus y, which is when you do evaluation to norm, the sign of the inequality will split. And this min becomes max. So norm of the sum of two, the PI norm of the sum of two elements is less equal to the max of the maximum of the norms. So this is actually stronger than usual norm inequality in the sense that usually we usually see something like norm of x plus y is less equal to norm of x plus norm of y. Now this is much stronger. It says that norm of x plus y is less than the maximum of norm of x and norm of y. It's much stronger. This is called strong triangle inequality. This is somewhat important in the sense that usually we can do analysis, diffusion analysis over the real numbers. We can also do analysis over the PI numbers. The advantage of the analysis in the real numbers is that you have to keep track of the convergence condition. You have to add up the partial sums. And because of this stronger triangle inequality, you don't have to check the partial sums. You just need to check through each single term. The norm goes to 0 and you're done. So just kind of a remark of why that's coming to be. Also, another remark I want to make is that if you play with this triangle inequality, you can show that if x and y have different PID norms, the norm of their sum is not just less than or equal to the max of the, it's actually equal to the max. The correlate of this is sort of triangles in periodic metric are isosceles. Two sides of this must be equal, at least two sides. But you can't talk about sort of IQ. So that gives me, I hope that's given you some sense of what the PI norm looks like. In any case, we define a metric on the rational numbers. Now, I define ZP with a PID completion. FC under the metric we just defined. And similarly, QP with a PI completion of Q. Okay. So I'll stop here and continue next time, talking about more about the PI numbers.